This is the lecture for Wednesday, April 8th. We will be talking about the quark-gluon plasma. These slides were written originally by John Harris at Yale University. So we will be discussing the primordial quark-gluon plasma, and I'll explain why we say primordial, at the relativistic heavy ion collider, RHIC, and the Large Hadron Collider, the LHC. So RHIC, the relativistic heavy ion collider, is located at Brookhaven National Laboratory in Long Island, and it turned on in the year 2000. And there are various detectors here that have associated collaborations. Okay, there's the STAR detector, there's the Phoenix detector, and the energies for the for RHIC are the collisions per nucleon are about 5 to 200 gigaelectron volts. Now, the Large Hadron Collider started doing heavy ion collisions from about 2010, and they do high energy collisions where the per nucleon energy is about 2.76 tera-electron volts. So that's a factor of one. So a tera-electron volt is 1,000 gigaelectron volts. And then in 2015, with the energy upgrade, it went up to 5.5 tera-electron volts. And there are various detectors and collaborations here. There's for the Higgs particle that we discussed, there are these detectors like ATLAS, and there's a large group at Michigan State that works on ATLAS. There's also a CMS collaboration that also does Higgs physics. Now the ALICE collaboration focuses on quark-gluon plasma's heavy ion collisions, and that's what we'll be talking about. There's also another collaboration, a detector, LHCb, where they do heavy quark physics. So the focus of today's lecture, though, is to investigate the properties of hot QCD matter at temperatures of about 150 to 1,000 megaelectron volts. So here's just some physics background of various exciting things from the year 2000 to 2010. You can see the Large Hadron Collider and quark-gluon plasma makes this list of things. You can see some of the other things that were hot during that decade, the decade of carbon, these negative index refraction materials, these metamaterials that seem to make objects disappear by bending light around and around things. The Wilkinson microwave anisotropy probe that looks at the heat signature left over from the Big Bang, and then quantum teleportation, okay, things like that. But we'll focus on the quark-gluon plasma. First instances of after the Big Bang, all matter as hot quarks and gluons, and this is now the main machine that's used to study the quark-gluon plasma is the Large Hadron Collider, and this has been a very successful machine that's done all sorts of things, from Higgs physics to heavy flavor physics to searches beyond the Standard Model to now heavy ion collisions. Here's a sketch, a picture from National Geographic. Here is trying to show the early universe. There is some point in space and time. You can think of space and time as flowing out from this center, this origin here. Okay. In the beginning, there's some Big Bang. We don't really know what happened in the Big Bang, but there's this very early expansion that we call inflation that happens, where through something called the inflaton, we won't talk about cosmology here very much, but there's a very rapid expansion of the universe that made things uniform. Now, after this rapid inflationary period, things started to cool down a bit, and we ended up with the quark-gluon plasma. Okay, so we're still at a temperature of about well, here you can see 2 times 10 to the 12 kelvins. About 10 to the 4th Kelvin is an EV, so this is about 200 megaelectron volts in temperature, and this is about 10 microseconds after the Big Bang. where you have these quarks and gluons and leptons. All right, and then later on you have the hadronization. You have then the formation of these hadrons. You can see the Qs are supposed to represent quarks. Now the Qs are bound together into baryons and pions and mesons and other things like that. And this is also showing the divergence of the four forces. So you have gravity, electromagnetism, the weak interaction, and the strong interaction. You can see electromagnetism and the weak interactions. They are actually unified by the standard model. It's only at some later stage in the universe where there's a spontaneous symmetry breaking, where these two split apart. Now there's a question whether the strong force can be unified with the weakened electromagnetic force. That's an open question still. And then there's also a question whether gravity can be unified with the other three. So the grand unified theory is the hope that the strong interactions can be unified with electromagnetism and the weak interactions. And then the theory of everything is the hope that gravity can be unified with the other three. Okay, so one way to study the properties of the quark-gluon plasma is to do lattice quantum chromodynamic simulations like we've been discussing. Okay, here are some results, and this author here, Alexei Bazarov, he's a professor at Michigan State, and he was involved in this calculation in 2009, where they measured what you see is the energy density divided by the temperature to the fourth power as a function of the temperature measured in megaelectron volts. And the reason this is useful is that for a relativistic system, as you go to high temperatures like this, eventually you plateau to a value that corresponds, when you take the energy density over the temperature of the fourth power, you get a measurement of the number of degrees of freedom that you have. So you can see it's plateauing to something around 14-ish degrees of freedom here. But you'll notice that at colder temperatures, so that's at about maybe 300, 400, 500 megaelectron volts, but at colder temperatures you get a much lower value, which is consistent with the confinement of the quarks and telling you that the degrees of freedom here are nucleons. Okay, so on the order of maybe 4 degrees of freedom or something more than that. Okay, but here you have something on the order of about 14 or so, consistent with having quarks and gluons. All right, so there's this critical temperature where this energy density versus temperature has sort of this inflection point where it rises rapidly, and that's the critical temperature, and that's something around 190 megaelectron volts, and there's a critical energy density that corresponds with this point here. It's about 0.3 to 1, or something on the order of about 1 gigaelectron volts per cubic femtometer. Here you also see a plot of the pressure, 3 times the pressure over temperature of the fourth power. As you get to high temperatures, you expect the energy density and the 3 times the pressure to overlap with each other. And these are just different data done with simulations done with different lattice actions, different ways of representing the physics on the lattice. Okay, here is a plot, again from Lattice QCD, where they measure the modifications to the QCD coupling constant, alpha S, as a function of the temperature. So what they do here, even though it says QQ, this is actually Q bar Q. They're measuring the coupling between a quark and an antiquark at a given temperature. So what they do is they measure the potential between a heavy quark and an antiquark. You just have a quark and an antiquark. Okay, and you measure the potential here, and you measure it as a function of the temperature for different temperatures, as a function of distance separation. So you can see here you have confinement. Let's start off at cold temperatures. You have confinement here. But then you turn on the temperature. This is as a fraction of the critical temperature. And so as you approach 1, you notice that these curves, you can see the symbols here corresponding with decreasing the temperature more and more and more. And you see at some point it no longer rises and it just plateaus. And this is evidence of what's called deconfinement, that this confinement property goes away once you have a high enough temperature. So you can think of that as there's enough energy, there's enough thermal energy that you have pairs of quarks and antiquarks being popped out of the vacuum, and so that sort of screens this whole quark-antiquark confining potential, and so that allows the quark and the antiquarks to decouple from each other, because the idea is there's lots of quarks and antiquark pairs just floating around because you have this hot system. And so there's no reason why these guys should want to be confined with each other. Okay, so this is these three gentlemen you've seen before, David Gross, Henry David Pulitzer, and Frank Wilczek. They won the Nobel Prize in 2004 for the running QCD coupling constant. And now, so this understanding of asymptotic freedom, right? This work from the early 1970s. This gives us a way of trying to understand what's going on, because at high energies we have some notion that the QCD coupling gets weak, and we can have some theoretical understanding of what's going on here. Now, here's a quotation from the Nobel lecture of David Gross. So before we had quantum chromodynamics, we could not go back further than 200,000 years after the Big Bang. Okay, and that's because we had to wait until things cooled down to the point where we had atomic systems, so we could study things from the atomic level. But now, today, since we understand QCD, that simplify, and we know that QCD simplifies at high energies, we can actually understand the early times of the universe when the nucleons melted to form, were in the melted form to form a quark-gluon plasma. Okay, they started off in a quark-gluon plasma, and then they eventually cooled down as nucleons. And so here's kind of a cartoon picture of the quark-gluon plasma as some sort of a soup. All right, you can imagine having so here's little Campbell's quark-gluon soup. So in the standard model, you can produce this quark-gluon plasma in various different ways. You can do lattice QCD or lattice gauge theory calculations that predicts that the phase transition is at about 175 MeV, megaelectron volts. From cosmology, you can actually try to look for this quark-gluon plasma, this quark-hadron phase transition in the early universe, try to look for remnants of that effect. And perhaps you can try to see this in the, well, this is more speculative, but nobody knows, but perhaps in the cores of dense stars, hot stars, you can see some of these quark-gluon plasma properties. But the question is, how can we make it in the lab? So the idea is maybe you try to heat up, you try to heat up these nucleons, or you bang them together and you form some sort of quark-gluon plasma at high temperatures, such. So that's the idea here. So here's sort of the Back to the Future character here. How can we make a quark soup? So here is again the early universe. Okay, so this is the temperature. This is about 100 megaelectron volts in temperature. This is the time after the Big Bang. Okay, and so you have here a few about 10 to the minus 4 seconds or so. You have hadronization, but before that you have the quark-gluon plasma. Okay, and you cool down. After hadronization, the quark-gluon plasma starts to confine, and the quarks into hadrons. You have baryons and mesons, QQQ or Q bar Q, and then eventually you have the nucleons start to form nuclei. That's nucleosynthesis. That's what happens here. That's what FRIB is all about, to understand this nucleosynthesis process either in the big early universe or in stars. Okay, now at some point then later you also have the formation of atoms, when the electrons are now have cooled down and are captured onto the nuclei, and then that's where we are here now. And so now with accelerators, though, we can zoom back up to a very high energy scale by banging these heavy ions together in these heavy ionic colliders. That's how we do it. Okay, so how to make this quark soup? Let's go in detail. So we have the strong nuclear force, which confines quarks and gluons to be in particles like this. The quarks confine inside here. But what we can do is we can compress or heat the nuclei to melt this vacuum, right, to make your quark-gluon soup. So that's the idea. We're going to try to heat this up, and so the quarks are going to try to liberate amongst themselves. Okay, so let's talk a little bit about the relativistic heavy ion collider. So as I mentioned, since the year 2000. Okay, so now you can see a little bit more clearly. You have Star, Phoenix, Phobos, and Brahms. Okay, and here's just the initial accelerator that they used to see the heavy ion collisions. Okay, so now they have these ions going at 0.99995 times the speed of light. Okay, so what they do is they typically do, well, they do lots of things, but what they typically do is gold-gold collisions. Okay, and each gold has 197 protons and neutrons that are accelerated. By the way, now they've done much more than that. So they've done proton-proton collisions. They've done proton-aluminum collisions, proton-gold, neutron-gold, copper, and copper-gold, and a few other combinations. So if you are not familiar with where exactly it's located, the relativistic heavy ion collider is on Long Island, about here. Okay, here's New York City. And now I'm going to show you some of the detectors that are used. So here's the STAR detector. This is the solenoid tracker at RIC detector. And so you can see these are ladders that people climb up on. So you can see the scale of it. And we have this forward time projection chamber, and you can see sort of a blown apart picture here. We have the magnet here, and you can see at the center we have the silicon vertex detractor, and then we can measure the time of flight. We have the time projection chamber here, as well as the calorimeter on the outside to measure the energy deposited. Okay, and so you can measure then from 0 to 2 pi in this azimuthal angle phi. So they're measuring lots and lots of stuff when they do these heavy ion collisions. So they have to be able to collect the data very, very rapidly. So you can see the actual STAR detector here in real life, like this. Okay, so it's kind of an impressive device. And here is a picture with the STAR collaboration and all the people standing here. Okay. And here is the typical event that you see in a head-on collision. You see this beautiful spray of particles that are being detected. All right, you have these. You can see the tracks. You can read off the energies from the calorimeter. That's quite impressive. Now, I'm going to now just make the transition to the Large Hadron Collider. We'll just briefly talk about the Large Hadron Collider, but we will pick it up next time, the serious discussion of the Large Hadron Collider for heavy ion physics. But for the heavy ion collider, you can do heavy ion physics. You can, even though ATLAS and CMS are focused on Higgs physics, they can also see these heavy ion collisions. Although ALICE is more is really set up to do the heavy ion collisions. So here's just the ring at the Large Hadron Collider. You can see the mountains, the Alps, Swiss, and the French border here. This is, by the way, you can see here a view from Hollywood. So you may remember the Large Hadron Collider was featured in the the movie Angels and Demons. You remember, this is actually from the movie itself, that they were talking about this whole antimatter bomb that was going to destroy the Vatican. So if you haven't seen the movie, it's a pretty entertaining movie. So next time we'll talk more about the Large Hadron Collider. We'll talk about the LHC Heavy Ion program. We'll pick it up from here. Okay, we'll talk about ATLAS, CMS, and ALICE. And I'll talk to you then.